Preparing for the future by studying the past. Researchers are now able to resurrect antibodies to the 1918 influenza pandemic from elderly survivors. How does technology used to do this potentially lead us to antibodies for other viruses? Can we be sure this immunity is not generated by recent exposure to similar strains? You are listening to ReachMD XM157, the channel for medical professionals. Welcome to the Clinicians Roundtable. I am your host, Dr. Mark Nolan Hill, Professor of Surgery and Practicing General Surgeon, and our guest is Dr. James Crowe, Jr., Professor of Microbiology and Immunology, and Director of the Vanderbilt Program for Vaccine Sciences at Vanderbilt University School of Medicine. Dr. Crowe is the senior author on research published in the journal Nature on the cultivation of antibodies from survivors of the 1918 influenza pandemic. Welcome, Dr. Crowe.
Thank you. It's great to be with you.
Dr. Crowe, could you give us a quick overview of your research with respect to the efficacy in mice?
Sure. Well, we're able to isolate antibodies from pandemic survivors in a way that we had single antibodies in our hand. These are termed monoclonal antibodies. So the antibodies only recognize one target, and that target is the hemagglutinin or HA protein on the surface of the 1918 flu. So having that highly specific reagent, which is almost like a biological drug, we were able to give these antibodies to Dr. Terry Tumpy at the Centers for Disease Control. And in a high-security, high biocontainment facility there, he infected mice with the resurrected 1918 virus, the virulent virus, and he did it in a way at a dose that would surely kill them, and the untreated mice all died. But at 24 hours or a day after exposure, he was able to treat mice with each of the antibodies that we isolated, and the antibodies reduced the amount of virus in those mice and actually saved them. And at the appropriate doses, each of the antibodies could save all of the mice that were challenged.
And how do you compare these strains to the 1930 swine outbreak or 1943, 47, 77, 99, all of these outbreaks? Are there similarities? Is it useful?
Well, I think we're all aware that flu comes around every year, typically in the United States, and it's a winter epidemic, and so we've all had experience with year after year hearing about or seeing flu every year. There are changes in the influenza strains each year, and that's why we all have to be re-immunized every year, immunized with a new vaccine. That's because the viruses have mutated slightly, and this is called antigenic drift. There's a slow drift. But every 30 or so years, a major change in influenza occurs, and a new type of virus comes, usually into the population from birds, and this would be called a major change or an antigenic shift. And when you get a shift, everyone in the world is susceptible because no one's ever seen that virus, and that's when we get everyone being infected, or that's called a pandemic. So when we got the antibodies to 1918, we went back to look at other viruses that had caused pandemics in the 50s or 60s, and then we also looked at representative viruses throughout the 20th century that were the same type as the 1918. And really, we did not find a lot of cross-reactivity between these antibodies. They really only seemed to recognize the 1918 virus and the 1930 virus, which was a similar virus to 1918 because these viruses circulated for several decades in the early 20th century.
Well, why do these viruses, these very virulent viruses, occur every 30 years? I mean, why?
Well, there appears to be an accumulation of immunity in the population to the circulating influenza that is around at any one time. And right now we have three types of influenza circulating. H3N2, H1N1, and B are the names of the three types that are circulating, and these are the three that are in our annual vaccines. And once you accumulate enough immunity, there seems to be a tendency to lose susceptibility as a population to that particular flu. But there are many types of flus that are in birds and animals, dozens of them. And if we go into bird populations right now, we can swab birds and find lots of different flus, and we also find flus in pigs and other animals. And we think what happens is a human being that's exposed to some type of bird flu that's already there in the birds becomes infected, and either that virus mutates so it can infect people, or it actually mixes and matches with a human virus that's in that person at the same time. And one way or the other, by mutation or by a mixing event, we get a new virus that's never been in the human population, and it spreads like wildfire.
Now, why birds? Why not an animal that is much closer to us, like a pig or other animals? Why a bird?
Humans and birds use different types of receptors to bind influenza. There are sialic acid, which are carbohydrate molecules that serve as the receptors to which influenza binds, and they're linked differently in birds and humans. So there's an alpha-2,6 chemical linkage, which differ in the birds and humans. So the details aren't really important. It's suffice it to say they're different. So typically we would think bird viruses would infect birds and human viruses would infect humans. Right. Sometimes we see that there are rare isolates that appear to bind both types of receptors, and this may actually occur best in pigs, sort of a mixing, because pigs actually have both alpha-2,3 and alpha-2,6 receptors. So one thought is that birds infect pigs and human farmers or other people on farms infect pigs. If a pig is simultaneously infected with a bird flu and a human flu, they can sustain both of those viruses because they have both receptors. And it may also be that some bird flus can just jump directly, and that's what you hear about in the news right now with H5N1 bird flu that's been threatening to cause a pandemic the last few years. This is actually a bird flu that just crosses directly from a bird to humans.
Do you think that that is a real possibility of a pandemic?
Experts disagree on the likelihood of whether the H5N1 virus will cause a pandemic. Right now we know that with close exposure and a lot of virus in a bird, certainly humans can get infected. There's been over 300 cases documented in the world so far, and 2/3 of those have been fatal cases. So this is what raises concern. The good news is the virus does not appear to efficiently spread from person to person. It just spreads from bird to person. So that's why we have not had a pandemic. And experts disagree on what is the likelihood that a virus will get into a human being and mutate and become a virus that can spread person to person. If a virus did that, then we'd have a pandemic, and that's what people are worried about.
And how does the bird virus get into a human?
Well, people are exposed to birds very frequently. In the markets in Hong Kong, many types of birds are closely housed, and human beings are around those birds. So farming individuals or markets where live birds are sold, this is where you get this kind of exposure. Now, interestingly, birds are infected with flu in their GI tract, not so much in their respiratory tract. It's really a gastrointestinal germ, and really they're pooping out virus into the environment. And so if you look in Hong Kong, even in the water that's used to wash down these markets, you'll find the virus on the floor in the water. And furthermore, wild birds have these viruses, and they'll sit down into bodies of water. So there's a lake in Hong Kong where you can go sample the water, and you'll find the H5N1 virus in that lake water. So close exposure to birds is the predominant way it's transmitted, but these birds are spreading virus all over the place. So it's possible to have an environmental or a fomite transmission from an object that's contaminated with bird feces.
If you have just joined us, you're listening to the Clinicians Roundtable on ReachMD XM157. I am your host, Dr. Mark Nolan Hill, and our guest is Dr. James Crowe, Jr., Professor of Microbiology and Immunology and Director of the Vanderbilt Program for Vaccine Sciences at Vanderbilt University School of Medicine. We are discussing advances in the viral immunity stemming from survivors of the 1918 influenza pandemic. Dr. Crowe, looking at the big picture and your incredibly interesting research, what information will you learn that might help us in viral diseases in general?
One of the most important things we're learning from the antibodies we've isolated is the fundamental process by which antibodies actually kill flu viruses. So we gave our antibodies to our collaborators, Dr. Chris Basler at Mount Sinai School of Medicine in New York, and he was able to treat viruses with the antibodies that were displaying the 1918 protein and find viruses that would mutate and escape from our antibodies. And when we track down and see where those mutations are, that's the footprint of where the antibodies actually bind. So we've been able to figure out where on flu proteins should we direct antibodies, what part of the virus is vulnerable to killing. And so even though the antibodies that we've generated are to 1918, and that virus is not circulating now, we're learning lessons about how to kill flu viruses in general, and we're trying to incorporate this knowledge into strategies for new vaccines, for the seasonal influenzas that are around every year, and also for the bird flus that are threatening pandemics today.
Will we be learning any information that may relate to treating HIV?
Well, actually, it's interesting that you would ask. We've just recently received several $1 million to use the same technology that we're using in flu to isolate antibodies to HIV, and we've been able to do so.
Tell us about that.
Well, in the last year, we have used a cohort of subjects at Vanderbilt that's followed by Dr. Spiro Callums, and these are termed long-term non-progressors. So there are individuals who've been infected for, say, 10 years and have never taken anti-HIV drugs, but their viral load is very low. So somehow they're controlling the virus themselves with their own response. And we don't fully understand what is the basis of that, but one of the contributors may be antibodies. So we've obtained circulating B cells from these long-term non-progressor HIV-infected subjects and have obtained HIV-specific antibodies from them. And we're already trying to study where on HIV do these antibodies bind, and do these antibodies kill HIV efficiently, and so on. So the viruses are very similar in that they change very rapidly. So flu changes in a population year to year. In HIV, this is accelerated. The change happens within an individual, so every day the virus is changing. So the approach we're using in HIV is actually to obtain antibodies in the same individual over time, so to bleed them every 3 months or so, and to make new antibodies, and then to study them against their new viruses, and to find out, can a person's antibodies actually chase the virus that's evolving within them?
Can they?
Well, we don't know yet. We suspect that they do, but the research that's been done by others with serum testing suggests that the body's response is always about 2 months behind. So a new virus arises, and that's almost like a vaccine event. So we see 1 to 2 months later, you get a nice response of antibodies occurring in that person, but by that time the virus has already moved on. So this is a chasing event in which the person's always several months behind. And what we want to learn is how to predict where the virus is moving, get out ahead of that virus, and lay some antibodies down, sort of in the way that firefighters go ahead of a large fire and they'll burn a corridor in front of that fire so that when the fire reaches, there's nothing to burn. That's what we want to do is to get antibodies out in the direction in which HIV is moving so that when the virus hit that point, it couldn't continue.
I want to thank our guest, Dr. James Crowe, Jr. We've been discussing advances in viral immunity stemming from survivors of the 1918 influenza pandemic. I'm Dr. Mark Nolan Hill, and you have been listening to the Clinicians Roundtable on ReachMD XM157, the channel for medical professionals. Be sure to visit our website at reachmd.com, featuring on-demand podcasts of our entire library. For comments and questions, please call us toll-free at 888-MD-XM157. And thank you for listening.